We are happy to have Raphaël Rouquier from IAS and UCLA to give the second talk of today's workshop. So the topic of his talk is lax 2 tensor constructions.
Okay, thank you very much, and thank you to Jordi for organizing this week and the whole IAS program. So what I would like to discuss is how one can try to realize certain categories of interest in representation theory or maybe in geometry, how one can realize them, we can construct them using using some algebraic tools, somehow without bringing in complicated things. So very much like moduli spaces of complicated objects of a simple variety could be obtained. Right. So I'll start with a brief introduction to two representation theory. So the two here refers to the fact that refers to the level of the categorical structure. So usual representation theory deals with actions on vector spaces, which are zero categories, and those representations together form a category, one category. So now we're going to look at actions on categories. So all those categories together with the actions are going to form a two category. That's where the two comes from. So this is something you can do starting, say, in monoidal category. You can look at its actions. Like representation theory, it's interesting because there are interesting examples of structures to study the representations of. And what has arisen in the past 20 years now is that there are such structures arising from Kac-Moody algebras, in particular complex semi-simple algebras. So we start with one of those Kac-Moody algebras with the usual presentation with EI and FIs and a category. So what is the true representation? Well, it's going to be the data of some actions. So they are going to be, your category could be abelian, it could be just linear, maybe it's triangulated, and eventually, unfortunately, it needs to be a little more sophisticated, like A infinity or infinity category for certain things. So the action of these generators on the vector space are replaced by endofunctors of your category, which may as well maybe required to be exact or triangulated depending on the settings. And somehow where the theory is really interesting is that there are going to be some hidden symmetries. So it's not so much that you have analogs of those endomorphisms satisfying these Lie relations. So what is going to control things and to make the theory very rigid is the fact that these endofunctors come with certain natural transformations. So for example, this EI should come itself with a certain endomorphism. And if you compose two such self-endofunctors of your category, in one way or the other way, there should be a natural transformation between them. So you can, geometrically, you should think that the EI as having to do with some line bundle, as having to do with some correspondence, and X being somehow having to do with the first Chern class of a line bundle, and the tau somewhere has to do with some geometrical phenomenon, which could be, things really commute, or maybe there's a P1 fibration somewhere. And these are supposed to satisfy certain conditions. So for now, we see only, I'm going to talk about the most important part somehow, the part that's not something you see classically, which is the fact that these X and tau, they satisfy some sort of affine Hecke algebra relations, which are not quite affine Hecke algebra relation. You need some new kind of Hecke algebras that depend on the quiver. So in type A, you can get away without that, or affine A. But in general, you need to use those algebras that were introduced independently also by Povanov and Lauda. And next, well, you need some FIs as well, but somehow it's like representations of compactly groups or unitary representation. your EI is going to have an adjoint FI, and you put that as a requirement, an adjoint functor here. And so this FI comes as an adjoint, and you need to put, you don't need to put the self relation. Some of the consequences of the relation satisfied by these X and taus, but you need to put some communication between EI and FJs. And the map tau, when you use the adjunction, does give you a map between EI FJ and FJ EI. And using the adjunction, you get also some maps to the identity. Using X, you can also take more maps. And all together, somehow you can express these relations by saying on a given weight space, HI should act as a certain scalar, positive or negative integer. So you can express that as saying that there's that a certain map is invertible on a lambda weight space. So this is really, this theory is really made for say integrable representation, etc., with a weight space decomposition. And one of the first examples, so I should have put probably Joe Schwang's name there. I think I can probably. Oh yeah, it's not going to say that anyway. Is looking at finite dimensional rational representations of GLN in characteristic P. And there's an obvious endo functor, which is tensoring by the vector representation. And if you think maybe rather of the Lie algebra point of view, I mean, if you do fp bar to the n tensor some representation M on this tensor product, you have a Casimir action. So the Casimir really acts on the functor E. And if you start with finite dimensional representation of a GM fp bar, its eigenvalues are going to be in fp. And so you can break down this functor according to the generalized eigenvalues. That's something that people have done in representation theory for a while. You can also express these EIs in terms of translation functors. And so these various EIs are going to give rise to an action of the Lie algebra SLP hat. And so tau is the fact that tensoring by V E square has clearly a symmetry, which is swapping the two terms is the tensor product. And then you have to do certain projections to apply to get this tau. And so one of the reasons, so this, maybe I should say earlier, I mean, the reason this was introduced was to solve a problem in representations of finite groups, that conjecture of Brouet on blocks of symmetric groups and general linear groups. And this types of constructions have been used in a number of cases to study representation of Cherenkov algebras or super Lie algebras, activity modules for GLN, as we heard Simon Rich mentioned yesterday. So somehow endoing certain representation categories with this extra structure of two representations is going to enable proving, for example, that they're equivalent to other categories which maybe are constructed geometrically, or yeah, to various things. But there's another reason why this is of interest, and that goes back to an idea of Crane and Frankel in the early 90s. And that was to try to upgrade the three-dimensional manifold invariants introduced by Reshetikhin and Frankel after Witten to get four-dimensional invariants like Donaldson's. And so Crane and Frankel's idea was that instead of quantum group representations, we should, whenever we see a scalar, we should see a vector space. Whenever we see a vector space, we should see a category. One should really have these types of structure of two representation. But they didn't have an idea of what this should be. But so the expectation is that if you look at all those two representations, these two category, it should be some sort of braided monoidal two category. And modulo doing certain things. Crane and Frankel's idea is that one should get invariants of four-dimensional manifolds. And so this 2 rep G is something that you would associate to S1, the circle. To a circle, you associate two category. To two manifold, you're going to associate a category. To a three manifold, the vector space, and to a four manifold, a scalar. So one thing that can be done is the construction of a tensor product. Okay, so it can be done in this generality. And there is something interesting going on there, is that to do this kind of tensor, when you have a V and a V prime with this structure of two representation, you want to build a new category, V tensor V prime. But this does, the underlying category depends on the action. So the forgetful functor categories is not monoidal. So that's a 4D phenomenon. In 3D, we have a phenomenon which is that representations of quantum group going to vector spaces, we're not going to get something that is braided, but at least it's monoidal. So here it's not even monoidal, but at least restriction to the positive part is monoidal. So somehow we can construct the underlying category using only, say, the EIs. And so one thing I want to explain somehow in this talk is that from a field theory point of view, what one needs is actually, or even a tensor product, maybe I should say. I mean, when you have a Hopf algebra structure or a bi-algebra, using the coproduct, if you have two commuting actions on a vector space, you can make a diagonal action. You don't need your vector space or your representation to be itself a tensor product. And so one can do something similar here, except that asking that the two actions commute is not a condition, it's an extra part of the data. So you have a category and you have two different actions, and you put extra data expressing some commutation between the two actions. When you have that, you can construct, so it's a bit more general than this tensor product, but really the same construction. You can construct a new category which will have one of those structure of two representation. So what's something you can do in the categorical settings that does not make sense in the decategorified setting, in the usual setting, is actually go lax, and that's the title of my talk. And so having this compatibility, having this data for commutation of the two actions is a requirement that certain maps are isomorphisms and certain compatibilities. But you can say, well, let's assume we have those maps that satisfy the compatibilities, but they are not isomorphisms. They could, for example, be zero maps. And if you have that data, you can still build that category. So somehow from a decategorified point of view, from usual point of view, the underlying thing doesn't change, okay? When you do the diagonal action, it's still on the same vector space. Here it's changing, and it's a new category. So I've crossed partially the fact that there is a two representation. In general, you won't have any more action, but there will still be an action if you have certain requirements, even if the things don't quite commute. And that's something I will be discussing later. So this tensor construction, or this more general somehow diagonal construction, gives a way to construct new categories out of old categories. And so I'll give some examples, and I think there are a lot of interesting things that are probably obtained like that. So there is one, so I didn't tell you how one defines this tensor product or this diagonal category. So it's not very complicated, except that this is really happening at this construction is a construction somehow that's homotopical. So if you start with a honest abelian category, something nice, what this construction will return is an A infinity category. It's not going to return even, I mean, you could make it DG, I mean, you could, but that would be a little bit artificial. So this is all happening in, you have to somehow switch to the infinity categorical word or infinity word to perform that construction. So that makes things, even for SL2, which some of all the difficulty already appears in SL2, that makes things a little bit difficult. And for example, I have a candidate for a braiding, but structure of a braided monoidal category is a lot of data, and it's a little bit of, looks like a really daunting task to check that this would give such a structure. So what I will be discussing now is joint work with Andy Mannion, where instead of looking at Kac-Moody algebras, we're going to look at a super Lie algebra, just GL11, and there's a miracle that you can do things similarly, but the tensor product now can be performed in a rigid world. You don't need to go infinity categorical, and so that's very good. And the second point is that from the field theory point of view, a 3D field theory related to GL11 is something that produces the, doesn't really exist, something somehow associated with the Alexander invariant of knots. And that has a categorical, comes from a categorical construction, which is Hegarth-Fleur or bordered Hegarth-Fleur theory, or not Hegarth-Fleur theory. So in the case of knots, it's due to Osvar-Szabó and the third person, Rasmussen. But so knots have to do with 3D, and what I'll be discussing will be only 1 and 2D. So I'll be, before talking about GL11, I was talking about surfaces, about some of things having to do with Hegarth-Fleur theory, because that's really where our work comes from. So what I've drawn are so the gray part are certain surfaces with boundaries. And so there are so-called sutured surfaces. So the boundary as a color, the boundary is partitioned into submanifolds which are either black or green. And there are finitely many intersection points. So that's a sutured surface. And then on top of that, we are choosing an arc decomposition for the surface, which is encoded by those red lines. So I'll be quick about that. I don't want to say too much more, but so for example, the two surfaces on the left are the same as sutured surfaces. It's just we've given different arcs, red arcs. And the third and the fourth one are both disks, but they are not the same as sutured surfaces. Okay, they're the same as surfaces, not as sutured surfaces. So Hegarth-Fleur theory is some sort of four-dimensional quantum field theory. So it associates a number to certain four manifolds, a vector space to three manifolds. That's the original theory. So using some sort of Fleur cohomology theory. And it's been extended to dimension 2 by Osvar-Szabó, bordered Hegarth-Fleur. And so that's what this is referring to. So there are additional structures on the manifolds that are needed. In the case of surfaces, it's not so complicated. So the structure of the surface can be, with this sutured surface, with this arc decomposition, can be encoded in essentially in something called an arc diagram. So here I'll call that a singular curve. So you keep the green curves, and the red lines, these arcs, will correspond to making an intersection. Okay. So on the left, you had two circles and an interval, same in the middle, they intersect differently. So if you go towards the right, so the force, the disk with this arc going through the middle circle is giving rise to something that has just one component. From sense, it's an interval, but that's self-intersect. And in the right, this genus one surface gives this S1, which has been folded onto itself twice. So we look at these pictures as some sort of one manifolds with singularities, and the singularities we allow are transverse. It's not so bad, and everything should be oriented as well. And associated to such a singular curve, together with a set of points. So you see here, we have those red points, which are exactly the singular points, but you could throw in more points. You can associate a category. It's very easy to define, where the objects are those are sets of those red points, not all of them. And the maps in your category correspond to looking at paths between collection of points. So if you just take 2 points, hum between these 2 points in your category is just vector space with basis homotopy classes of path, except that you allow only oriented path and you allow only smooth paths. So you're not allowed when there is an intersection point, you're not allowed to start from one component and bifurcate. You have to stay in a smooth direction. And composition is just concatenation. So sometimes the composition will be 0 if you arrive at a singular point with the first path, and then you compose with another path that goes in a different direction. Right. So this category has maps that are certain paths, and you can assign a degree to these paths with the homotopy classes, which has to do with the number of intersections. So in general, you have more than one path. You have several paths, a bunch of points, 2 collections of points and paths between them. So you can count intersections. But you need to do something a little bit more subtle, which is some sort of a Maslov index. It is a true Maslov index when this is interpreted in symplectic geometry. So this category is actually filtered, and you take the associated graded. And this is the category you want. This is the algebraic structure you want to associate to your singular curve. And so it's an F2 linear category. It has also a differential, which is obtained by resolving crossings. If you have 2 paths that intersect at an intersection point, the differential is going to resolve the intersection. So the differential is going to be a sum over all the intersections. And these algebras were introduced by Lipschitz, Oswart, and Thurston. So these algebras are really counting a number of holomorphic disks, so more general setting of Zarev, and this more general setting is ours. So a singular curve is something that need not even be oriented. It could have paths that are unoriented. It can have, you'll see why it's useful. And so this differential category, as was proven by Oru and Lekili-Polchuk, has it's the rough category. So you can put gradings. Gradings are rather subtle. The filtration is not the degree number. The degree is not a number. It's something with value in a non-commutative group. So everything is, you have to involve non-commutative groups, but eventually you can still make sense of complexes. I mean, there's still, it's not just a differential structure. And you can relate this to Oru proved that this is equivalent to a derived category of a Fukaya category, to Fukaya category, which is what you would do in, say, Fleur theory. So you take your surface and you take a certain symmetric power of your surface, and somehow that's what you will associate to your surface. So when you have a 3-manifold, which is with a Hegardt decomposition, you have a surface in the middle. In the symmetric power of that surface, your 3 manifolds will give rise to certain Lagrangians. Your 3 manifold cut in 2 pieces, and the hum between these 2 Lagrangians is the 3 manifold invariant you're going to associate. Anyway, so this category encodes not just a Fukaya category of a symmetric power of your surface, but it comes, these red lines are going to be strict. I mean, you can put a Lagrangian structure on your surface for which these are Lagrangian, a symplectic structure for which they are Lagrangians, and they will also give Lagrangians in symmetric powers, and these will be generators for your Fukaya category. So you have this differential category with the RAF category. It's the same as the Fukaya category, which comes with the symplectic manifold with this preferred set of generators. And it's not really Fukaya. You have to do some partial wrapping, which is precisely with this structure. So all of that, all those complicated holomorphic discounting, so the holomorphic curve business is encoded by this algebra. Right. So maybe one last thing. I mean, one can define directly a triangular category with no choices from the structural surface using contact geometry, and that's called as a contact category. But you get a huge, absolutely huge category. Right. So what curve can we take? We can take an interval which is unoriented. So put these double arrows to say it's unoriented, and we put endpoints, and order them 1 up to n. So what is this category A? What are endomorphisms from one end to itself? Well, there are just paths between these things, and of course this is simply connected. So path is determined just by the source and the target. So what we obtain in this category is basically the symmetric group permutations of the points. And so we can draw this as some sort of singular braid. But now we put a filtration on that category, which is really the length of the permutation in terms of Coxeter structure. So it's the number of crossings really of your braid. And when you do that, the associated graded, what you get is the nil Hecke algebra. You still have generators which are pictures, which are these singular braids, but parameterized by partitions. But now when you multiply 2 of them, if the lengths don't add up, you're going to get 0. Okay, so the nil Hecke algebra over F2, say here, doesn't matter, is a graded algebra of the filtration on the group algebra of your Weil group for the length filtration. And on this Hecke algebra, on this nil Hecke algebra, we have a differential that sends the generators of your Hecke algebra to 1. So you can do that for any Coxeter group. If you take the Hecke algebra, you put parameters so that the generator square to 0. This algebra has a differential where you send the generators to 1. And if your Coxeter group is not trivial, this algebra is acyclic, okay? Because T of 1 is the differential of something, so that's going to kill the cohomology of that algebra. Okay? So only in this setting there, only H0 and H1 are non-trivial, if you make sense of both of them. So these are this is a typical phenomenon in the theory, is that most of the algebras you're going to meet are acyclic. They are differential algebras and they have no cohomology. And the operations we're going to do, so what we do in our work with Andy is nothing is up to homotopy, nothing is, we never look at the cohomology, etc. Everything is on the nose. So some of the differential, you should really think of it as some extra structure, but you could, you should not try to think that you're looking at the cohomology, otherwise you're going to waste a bit too much information. Or you're getting into other issues which have to do with 3 manifolds. Right, so at last I can talk of GL11 plus. So GL11 is a super Lie algebra, endomorphism of a 2-dimensional vector space, which has 1-dimensional even, 1-dimensional odd part. And we're looking only at the positive part of that. So that's a 1-dimensional Lie algebra in odd degrees. So just take C as an odd Lie algebra, odd super Lie algebra. Its enveloping algebra is C of E mod E square. And Kovanov proposed a while ago, and inspired by actually by Hegar's theory, proposed a categorical version of that. So you take a monoidal category generated by one object E, and one endomorphism of E square, which satisfies the brain relation. It's a differential category. Differential of tau is a 1. So the objects of that category are powers of E. The endomorphism of a power of E is this nil-Hecke algebra as a differential algebra, which is, as we saw, acyclic for n greater than or equal to 2. So somehow, if you look up to quasi-isomorphism, E square is quasi-isomorphic to 0. And so somehow you have a category where you have the object 1, E, and then E square becomes 0. So it's like the enveloping algebra of this GL11 plus. Right, so what we did with Dumanion is this: we just studied the representation theory of this at the 2 level. So we studied categories acted on by U. And so you can do that using, for example, algebras. So you can fix the differential algebras and look at actions on that, which means you will have a bimodule and the tau as above. Okay. So the structure of a 2 representation on A would be just this. Right. So starting point somehow of the connection with Hegel-Floer theory is that if you take a singular curve with an unoriented interval somewhere in it, so I've drawn a picture. So the Z there on the left side of this unoriented part, and I've put some mark to say that afterwards there is a part that could be oriented, doesn't matter. But going down, you should have your full interval, and its closure somehow should be intersected, should be already contained in itself. So we don't want another part sticking out. So when you have such an embedding, you can define a structure of 2 representations, which I write in terms of categorical bimodule. So you can think of this category I defined before as an algebra with idempotence corresponding to this subset. So what this bimodule is given, a power of E is given by taking now path, not just from a set I to a set J, but J to which you adjoin these orange points. So these orange points, so we have to assume that there is no red points in this zone, so which we can, so I didn't write all assumptions, there are a few assumptions there. And we need an endomorphism of E square. Well, when you have path, say, ending at 1, another path ending at 2, you can composite with a path that switches 1 and 2, and that's the action of tau. It's a very simple construction. And so this, so if you take now an interval, unoriented interval, and you put countably many points, so say your unoriented interval is a real line, and the points are the integers. So the category you associate to that is actually equivalent to this category U above, where if you take a subset with n points, you map it to E to the n. And so our real line, there are 2 ends you could consider, the positive or the negative. So there are going to be 2 ways to give a 2 representation. And that's the same as what you would get starting from this monoidal category U. It acts on itself by left multiplication or by right multiplication. So we have somehow more geometrical way to, topological way to realize that. So, okay, so we have a notion of 2 representation of at least GL11 plus, the positive part. We have examples there. And so the idea is that this is going to be tied to a 2-dimensional field theory, which where somehow gluing surfaces is going to correspond to some tensor operation for categories. So if you start with your differential algebra, and if you have F1 and F2 giving structures of 2 representations, So we would want to construct, as I explained earlier, without giving a definition, a new differential algebra, or possibly with an action. So what we're doing that in the Slack setting. So we're starting with a map between these bimodules, which is compatible with tau 1 in the sense if you start with f1 square and you move it, you have an application of tau 1. Using lambda twice, you can move f1 square to the right of E2. And you assume that it's compatible with tau 1 and similarly with tau 2. So given this structure, you can construct a new differential algebra where you take the tensor algebra of this bimodule, f1 tensor E2. And so it's some sort of quadratic algebra construction. You factor out a certain subset of the degree 2 part of f1 E2, your bimodule squared. And so that's obtained somehow by forcing tau 1 and tau 2 as acting in the same way. So there is this tensor algebra of the bimodule f1 E2, f1 tensor E2, and a subset of f1 E2 square, which we take as relations for our new algebra. So that's a new differential algebra, which depends on lambda. And as before, I mean, if we have an adjoint to if one, any one, lambda is, we can use the adjunction to get a map between e's, which we call sigma, and I don't think, yeah. So now you have E1 and E2s, and if you extend E2 at just an action of A, you can, same with E2, you can extend scalars to B, so to make them into right B modules. And there's a canonical map from E2 tensor AB to E1 tensor AB. So by adjunction, it's the same as a map from F1 E2 tensor B to B, and that's just a multiplication map. So B is this delta algebra. So this cone is naturally a right B module and the left A module, but the action of A on the left can be extended to B. And if sigma is invertible, you can even define a tau on E square, and this gives a true representation. Okay, so that's a very simple construction, but that gives rise to fairly complicated structures. So one has to, what I'm saying there is not a full definition. So there are some assumptions. I mean, this makes sense. This is correct. But a good construction is more complicated than that when lambda doesn't satisfy certain properties. So what I will be talking about after is this better construction, but it takes yeah, it's a longer construction. Right. So now let me move examples. Well, so if you start with a singular curve and you assume that it has two ends, somehow there are two intervals you can embed unoriented. So this could be disconnected. So you can you will get two actions on the corresponding category, coming from both ends, and so you can perform this kind of diagonal construction. And so what we prove, so that's our main result with N-Dimanian, is that doing this operation is somehow is linking the two intervals and in a directional way. I mean, you're adding, you're gluing a segment which is gluing an oriented interval. So this tensor operation has some sort of field theoretic perspective. Here it looks one-dimensional, but really it's, there's something two-dimensional. So as an example, so remember this surface, which was a disk with let's say n holes, n punctured disk. So we have to look at the disk with all these structures, the suture structure together with the arc decomposition. So the blue lines means you're cutting the disks into pieces. So this is something you can do. So it's more reasonable with this suture structure, and plus arc decomposition structure. So what the theorem says is that you can recover the category associated to the full disk by gluing together categories associated to these small things, which are big disks with only one puncture on this arc thing. And so this delta construction, when it's two different things we're gluing, write it as a tensor product. So this theorem says that so you can reconstruct this category from the category you associate to a single puncture disk or to this singular curve, which in terms of algebraically, what is this category? Well, there are two subsets you can consider, just empty subset or just this single red point. And the path, there is no point, there's only empty, there's just one path, it's empty, you just do nothing. And otherwise, so everything is oriented. You can go around the circle n times from your red point to itself, and that corresponds to x to the n. It's a very easy somehow example. And what you get when you've done this tensor product is fairly complicated. So let me look at a different example. So I start with now these examples that correspond to the regular representation. Remember this monoidal category U with its left and right actions was the same as taking the real line with red points being the integers, unoriented. So we have two sides to the real line, two ends. And if we do this delta construction with respect to those two sides, the theorem above says that we get a circle which is unoriented except at some part where you have to force some orientation. So the original real line, so Hom spaces have to do with nil equialgebras. So what this operation has done is that it has added, now we can take paths that go around the circle. So we get, if we fix n red points, the endomorphism ring, we still have the old part, nil equialgebra. So the T1, Tn minus 1, now we have a new generator C that will correspond to moving around the circle or moving one up. And C itself is not invertible. Something that goes around the circle, there's an orientation on the left side of the circle, so you can't go back. And this is a subalgebra of a bigger algebra where you take the circle totally unoriented. And so you end up, so that's a picture on the middle, on the right side. You end up with a bread, singular breads drawn on a cylinder. So if you were to look at honest bread, you would get the annular bread group. If you look at the categories that I called A earlier, you would get the affine symmetry group. So there are n periodic permutations of Z. And so here we get a nil version of that. And so in terms of equialgebras, classical equialgebras, what we have is the nil affine equialgebra. So the nil equialgebra of the Coxeter group an minus 1 hat. So this nil algebra, this equialgebra is generated by T0 up to Tn minus 1. Okay, we have this affine equialgebra, and we force the generator to square to 0. And we throw in an additional element C, which is encoding the rotational symmetry of the affine Dynkin diagram. So we have this semi-direct product algebra, which is which is the algebra we get from from the unoriented circle. So, okay, so we have the algebra or the category for the unoriented circle. Inside, we have the one for the oriented circle, which corresponds, so in terms of Hecke algebras, we have our affine Hecke algebra, we extend with C, and we look at the subalgebra generated by T1 up to Tn minus 1 and C. And the theorem here says that gives us a presentation by General-Anton relation of this subalgebra, this plus part of this affine algebra. I think it's generated by the all the T1 up to Tn minus 1, which have to do with the finite part. You're throwing an element C and satisfies some obvious relations. CTI is Ti plus 1C when C is up to n minus 2. On the right-hand side, you have an extra generator T0, so you can make sense of that relation for all i's if you look modulo n. So here on the plus part, we can't do T0. T0 somehow violates the goes as a strand going in the wrong direction. So you put the additional relations that C squared Tn minus 1 is T1 C squared, which is obviously true. And then you have to prove that this is a presentation of this subalgebra, the Nilafan Hecke algebra. So that's something that's not trivial. It's not difficult. It's not trivial. So this gluing theorem that we prove with Onivanian relies on some proving some generator and relations in this general setting of singular curves. And there's something that you can do. So going from this plus version of the Nilafan Hecke algebra to the full one, all you need to do is to invert C. In this case, we're in a strange situation where there's still an action of E. Some kind of miracle happens. We still have a two representation on this category associated to the circle, just partly oriented. And inverting C corresponds actually to taking somehow E fixed points. Okay, we have this Lie algebra acting. If we take fixed points, we're looking at the part where E acts by 0. So in terms of in categorical terms, that means we quotient, we take quotient by E. E is somehow a two-term complex. We invert that map. So that corresponds to inverting C, and we get our algebra. So there's something not really, I would fairly mysterious here, is that you start with a finite Hecke algebra, and you perform this construction by somehow this diagonal construction, and then you take some fixed points, and you get the affine Hecke algebra. So, I mean, one can wonder, question whether these constructions from two representation theory, whether there is a way to use them to go from some more classical objects of Lie theory to their affine counterparts. So can you go from the flag manifold to the affine flag manifold, or representations to representation of an affinization? So here, closing this circle is indeed it's a bit reminiscent of taking some sort of you get an S1 by starting with an interval and somehow closing it. So there's something, there's possibly something, some explanation of that type going on here. But yeah, it would be interesting to do something to see if there's something like that can be done, for example, for affine Lie algebras or categorical structure. I don't know. So we'll finish by going to the back to this example of the disk with n punctures. So if you remember, we had another way to define an arc decomposition on that disk, which was by using arcs that connect the left-hand side disk was connected to the boundary, to the bottom boundary, but the other disks are connected between themselves. And then we can't slice the disk, we can't cut into elementary pieces because we're not allowed to cut one of those red arcs. So, okay, let me comment on that maybe now quickly. There's something some very strange happening. Should we say? is that the affine equialgebra of say, GLN can be embedded in the one of GLN plus 1. Because at the level of the finite equialgebra, you can embed the one of Sn in the one for Sn plus 1. And the level, if you think of a Bernstein presentation, you're just throwing in one more generator, and that makes an embedding of algebras. Now, if you look at different some of monoid in your affine bread group or different, you make the affine equialgebra without allowing generators to be inverted. You can see that this embedding doesn't work anymore because you have to go through exercise, and that forces you to invert certain generators. So this algebra Hn nil plus, you cannot really embed it inside the next one. But somehow the fact that there is still this action of E on this two representation has to do with the fact that you can embed it into 2x2 matrices. So the nil affine equialgebra of GLN for n can be embedded in the one from n plus 1 using these maps. The Ti goes to this diagonal matrix, and this C goes to this upper triangular matrix. So you can write this thing without inverting Ti's, so i's between 1 and n minus 1, and C. So you're not inverting those. So that's somehow a substitute for the usual embedding that requires to inverting some Ti or C. So sorry, end of the parenthesis, and I can go back to my disk. So there are two different, I introduced two different arc decomposition of this puncture disk, which correspond to, which will lead to two different singular curves. And the fact that somehow what you've done is just taking two different sets of generating Lagrangians for your Fukaya category. I mean, it's still the same Dirac category. You still have the same Dirac category. So these two, the differential categories you associate there are going to be derived equivalent. So also something you can check by hand. So the second one is not something you can describe as a tensor product. All right. So now what in onion conversion with Marangon Willis and with Lauda, they have probably a number of things about this bottom category, which is more complicated in some ways, but nicer in other ways. So first, it's formal, and its cohomology is something that has a nice description, which, well, they proved it was the same as an algebra introduced by Oswart and Szabo, also in Hegarth-Fleur theory, but to compute not Hegarth-Fleur cohomology. This is some of the crucial algebra, the cohomology of this bottom left category. It's a crucial tool, algebraic tool, for associating Hegarth-Fleur vector spaces to knots and links. And so what Lauda and Magnon showed is that this algebra is actually a deformation of some algebra that comes in Lie theory. So in some sense, it's some kind of equivalent version of what you would find in Lie theory from a parabolic category O for GLN. So this has to do geometrically with certain Springer fibers instead of the full somehow T star G mod P, the full codurgent bundle of a flag variety. And this is very close to a number of things that people, Oru, Smith, Abuzait, etc., have done in relating Hegarth-Fleur theory with various symplectic structures. And so this somehow same Dirac category has two not quite T structures, but there are two natural sets of objects that all form some sort of basis. So the one for the tensor product corresponds to a standard basis, whereas the one the bottom corresponds to a dual canonical basis, to projective objects. And so the one we're interested in is this one with a nice abelian structure, this dual canonical basis structure. So one that's easy to describe as a tensor product is the one with standard basis, and that's something you find in when you do tensor products for Kac-Moody algebras as well. It's a typical feature. But what's going on here is there are many more reasons. I mean, that makes this particularly interesting. And I'm running out of time, but a lot of work of Animadion has been devoted to understanding that, and eventually getting our framework to work in dimension 3 and recovering invariance of not Lagarde invariance of not from this categorical conception. So I'll stop here. Thank you.
Okay, listeners, thank you, Raphaël, for the beautiful talk. Are there any questions for Raphaël?
Hi, Raphaël. I like this embedding of the nth affine into the n plus first affine. I mean, does it work for, you did it for the nil version, but does it work for standard?
Oh yeah, sure. See, I should have said this. The fact that you get the generator relations and this embedding, absolutely it works if the TI satisfies their usual quadratic relations, but you can put any parameters. The parameters don't need to be invertible. Yeah, absolutely. Yes, absolutely. I have no idea what this means. Okay, this must mean something. And of course, the question we could ask is whether one can try to get the affine Hecker category from the finite Hecker category by some sort of trick like that. I don't know.
Yeah, there's an awful lot of difficulty involving these functors. Do you have any sort of, never mind. No, this is the hard direction. Never mind.
Are there any other questions? If no, let's thank Raphaël again.